place naturalistically, and then through meteoritic transport, that life on Mars got transported to Earth. But I explain in the book why that hypothesis has been abandoned, because Mars also is subject to the same oxygen ultraviolet paradox as planet Earth is. And unlike planet Earth, you don't have the plate tectonics to recycle the carbonates that are formed. And so what you have on Mars is what's called a carbonate catastrophe, which means if Mars ever was wet and warm in the past, those wet, warm conditions would guarantee that the carbon available for these prebiotic molecules would get rapidly and permanently put into carbonates. Whereas on planet Earth, those carbonates can be recycled. That can't happen on Mars. And so that's what caused the astrobiological community say, well, if it can't happen on Mars, then maybe it happened on one of Jupiter's moons or one of Saturn's moons. And I won't go into all the details, but there's even sounder reasons why those are not possible sites for the origin of life, which has now led the astrobiology community to say it must be another planetary system or it must be an interstellar cloud. And indeed, in interstellar clouds, we do detect over 120 carbon-based molecules, many of which would be important for prebiotic chemistry. On the other hand, we see no amino acids, and we see none of the 5 or 6 carbon-based sugars that are critical for DNA and RNA, nor do we see the nucleotides, the building blocks of DNA and RNA. Now, when I say that, I'm not claiming that's always going to be the case. We're only able to measure those quantities down to parts per billion. It could be when we get down to a few parts per billion, we'll actually detect those kinds of molecules in the interstellar clouds. Because we do know that there's chemistry there that should make the nucleotides, maybe not the sugars, but the nucleotides and the amino acids at a very low abundance level. But a low abundance level is useless for a naturalistic origin of life model. As Carl Sagan pointed out, you need a concentrated prebiotic soup. A thin soup is going to be of no benefit. And I also discuss in this chapter what's called the homochirality problem. The problem, and this is one of the simplest things for the origin of life naturalists to really resolve, is the problem of getting all the amino acids lined up left-handed and all of the sugars for DNA and RNA lined up right-handed. And there's no mechanism naturalistically either on the Earth or in interstellar space that can make molecules that are 100% of one hand as opposed to the other hand.
That arrangement is critical for life?
It's critical.
Okay.
If you don't have 100% left-handed or right-handed, then you're not going to be able to put the amino acids together to make proteins or the nucleotides together to make RNA or DNA. They all have to be of the same handedness. And the closest astronomers have been able to come to finding a mechanism that could work would be the circularly polarized ultraviolet radiation that's emanated from some black holes and neutron stars. On the other hand, that's a deadly environment for prebiotic chemistry, and even then, you do not get 100%. The best you can get is a few percent, and a few percent is not adequate. You need 100% away from the 50-50 mixture.
Yeah. Hugh, you got a little technical for a layperson there, but it sounds like you're talking about the various building blocks necessary and the difficulty in finding those not only here on Earth but in nearby solar system bodies. Now, there are those who follow the news. Anybody with any following at all of the news is going to hear often about discoveries of water on Mars and possibly other moons, and the connection is made from water to life. Why is that not a plausible scenario?
Well, water is the second most abundant molecule in the universe, and as we just talked earlier, there's a problem if you got too much water.
Yeah.
And what you need is a planet with a tiny amount of water where water exists on its surface in all 3 states, liquid, vapor, and ice. And that's the unique feature of the Earth. But keep in mind, it's only one requirement for the origin of life on planet Earth. There are hundreds of others that also must be met.
So even if you had a very nice supply of liquid water in the right abundance on another body, you still need, how many other features did you say?
Several hundred features.
Okay.
That must be fine-tuned.
Have any of those been identified?
No.
Okay, so we got problems.
Well, I mean, an analogy is this. You can put a pot of water, sterile water, on the stove, and leave it there under sterile conditions and see if you're going to get the origin of life.
Okay.
I mean, water by itself isn't going to do anything.
Yeah,
You need a lot of other ingredients in that water to make life feasible. Then you need some kind of naturalistic pathway that's going to assemble the molecules, and that's what we're not finding.
Yeah. Now, Hugh, you have talked about studying the moon. Why is that important in terms of putting competing life models to the test?
Well, we argue that you're never going to find fossil records of Earth's first life on planet Earth. That's because we know that between 3.5 billion years ago and 3.8 billion years ago, the geology of the Earth was far more active than it is today. And that active geology would effectively destroy the fossils of Earth's first life, circa 3.8 billion years ago. On the other hand, that was also a period of time when the Earth was experiencing fairly intense asteroidal and cometary bombardment. And as a result of that bombardment, we would expect significant quantities of terrestrial material being transported to the moon. In fact, I refer in the book to calculations of how much Earth material we should expect to find on the surface of the moon. And we're talking thousands of tons per 100 square kilometers, tens of thousands of tons actually. And therefore, it wouldn't be that difficult to go to the surface of the moon and recover Earth material that's been laden on the surface of the moon and find within that Earth material the fossils of Earth's first life. Because unlike planet Earth, the moon has virtually no geological activity, which means that stuff that was transported there from Earth 3.8 billion years will still be there in pristine form.
Wow, okay. Hadn't thought of that.
Well, a couple of astronomers actually calculated what would happen to Earth life that gets transported to the moon. And they're able to show that a lot of that material would have been colliding with the moon at a fairly high attack angle and a low enough velocity that the fossils of Earth's first life would remain undisturbed. So the collisions themselves typically are not going to destroy the fossils.
So you're suggesting that if we look hard enough, we'll find these materials on the surface of the moon, and we'll learn more about Earth's history and maybe about the solar system's history?
Well, for example, we have NASA proposing to look for life on the surface of Mars. And I would argue if they look hard enough, they'll find it because that's Earth-transported life.
Okay.
But Earth-transported life is far more efficiently transported to the moon. It would be a real long shot for NASA to find the remains of Earth's life on Mars, although I know it's there. But it's there in such low abundances, it's going to be extremely difficult to actually discover it. But on the moon, it should be relatively easy. And moreover, it's a lot cheaper for us to go to the moon and look for that stuff. But the bottom line is it would settle a major dispute in creation and evolution. It's an enormously powerful test because a naturalistic model predicts that Earth's first life will be orders of magnitude simpler, that it won't be that abundant and it won't be diverse. We're predicting the opposite. By going to the moon and recovering the fossils of Earth's first life, we'll be able to tell who's right and who's wrong.
All right, so another way to test the model.
It's another way to test the model.
Great, sounds good. Okay, Hugh, anything else in this chapter, or should we look forward to the next one?
Well, there's a lot more in this chapter.
Yeah,
it's one of the
sure
more
there is.
fun chapters I wrote.
Yeah, so you've taken us from the universe to the galaxy, solar system, Earth, and what are we going to hit on the next
Well,
time?
in Chapter 10, we're going to look at the history of life on planet Earth. Not the soulish life that we see in birds and mammals, but all the